My name is Abbas Acar, and I'm going to be talking about our IoT cryptojacking detection paper, which we presented in NDSS. And I'm going to be starting the presentation, and in the middle of the presentation, I'm going to give the microphone to my co-author Ege Tekiner to present our experimental size or data collection part of the paper, and then we will continue about the evaluation. This is my outline. I'm going to be starting with the background on the cryptojacking malware, and then I'll be explaining IoT cryptojacking malware as well as the existing detection methods. And then I will be explaining our approach in this study. Then I will explain our threat model. Then we will go over with the implementation, setup, devices, and dataset collection parts. Then we will explain the details of the benign and malicious data collection. And then we will explain our evaluation as well as the experimental challenge that we had throughout this study. Then finally, I will show some of the code we shared in GitHub, as well as I will finish my presentation with the concluding remarks. So what is cryptojacking? Cryptojacking is an act of using victims' processing power without their knowledge and consent. It's actually same as the crypto mining. However, here is the difference is the victim doesn't have the knowledge and consent for the crypto miner. And some of the examples that we found in the media is some samples found in the US DoD or UK governmental services, as well as some YouTube also compromised and became the victim of this malware, as well as we have seen the examples of Nintendo game consoles that has been used as a victim of this malware. And there are actually two types of cryptojacking malware. One is in-browser cryptojacking, another one is the host-based cryptojacking. And in-browser cryptojacking malware takes an advantage of interactive web technologies such as JavaScript or the WebAssembly, and then it connects to the victim's host devices to access the computational resources of victim, and it performs mining as long as the victim keeps the web page open. And the way it works is the user access to the infected web page, and the web page calls the mining script that is actually provided by a service provider. Then this service provider receives the task from a mining pool, and which assign it to that victim. Then at the end of the mining computation, then the results are returned to that service provider. Then service provider sends the results back to the mining pool. Then if the result is valid, then the reward is returned to the malware owner, not to the victim. So the malware owner benefits from this attack. On the other hand, the host-based cryptojacking malware, the host-based cryptojacking malware turns victims' host devices into a miner for the malware owner. And the way it works, actually, in general, they merge this cryptojacking malware with a normal, like for example, some game binaries. They merge into together and they share it through the internet. And the way they spread it is in general like malware advertisement methods or peer-to-peer sharing methods. And then in this one, the difference between the in-browser and host-based cryptojacking is the malware needs to be deployed in the host device. So the attackers in general are using either the methods such as social engineering methods or some compromised or some exploitation, that known exploitation, to deploy the malicious malware into the host device. And when it comes to the IoT cryptojacking became the new favorite toy for the attackers. However, they're not generally profitable individually because they're resource-limited devices. However, these days, the attackers in general are using the botnet attacks to deploy them at scale, and they're actually using the already existing networks, and then they're using the miners as a side profit. One example of this is Mirai-inspired botnet attacks. and the attacker used this to turn the botnet network into a giant cryptojacking mining pool. And we have seen actually follow-up examples. For example, LIQUOR IoT botnet started to mine Monero on its victims' IoT devices, and these botnets have already the network in their control. So they're just using a new functionality to have another profit on these devices that already have the control on. And some more examples are Bash Lite updated with the mining and backdoor comments to benefit from the networks that it already has. And more examples we have seen recently just before coming to presentation when we search. We have seen enemy bots, Spring4Shell or Gulub Teba and Tickbot. These are the well-known botnets that's been already deployed, but recently they just started to turn their networks into weaponize their network to mine cryptocurrency. And when we look at the literature, some of the existing solutions for the cryptojacking detection is the features are based on for example, hardware level features such as CPU events, memory activities, hardware counters, or system calls. However, these are not applicable to the IoT devices because in order to monitor or save, record these features, you have to deploy a software on the IoT devices. And these IoT devices are very limited and they don't run this kind of software in general. And on the other hand, some of the existing solutions in the literature focus on the browser-specific features such as JavaScript compilation time or static source code analysis. However, these features also are not applicable for IoT cryptojacking because these devices do not run a browser at all. So in our approach, we use network traffic because in order to capture the network traffic, you don't need to program each IoT device. And you can actually collect the network traffic for all device types, communication protocols, or hardware types, which makes it a powerful feature to use for the IoT malware detection. And it also works on the encrypted network traffic because you can only use the metadata for the malware detection. However, this approach and IoT cryptojacking in general is challenging because of the evasion techniques that are used by the cryptojacking malware, such as CPU limiting. And also these IoT cryptojacking malware in general are incentivized to use the minimized communication to hide the operations. And because of the high device diversity and heterogeneous traffic that we're gonna have from the smart environments, this approach is also challenging. And we have two threat models in this study, and first one is the cryptojacking with the service providers. And in this one, in the previous study, we found most of the malwares are sourced from specific service providers. And we used some of these sources in order to create our implementation. So this threat model including attackers also do the same. So this threat model including this implementation in which we use the scripts provided by the service providers such as Coinhive, Coinimp, or webminepool. And in this study specifically, we use webmine and webminepool scripts. And the second threat model is including a CC server. In this one, for example, compromised IoT devices receive the task from a CC server. Actually, this is the same CC server as it is used by the botnet. And this task is, in general, they're taking it from the mining pools. And then the results returned by the devices are, if they're well-lit, then these CC servers are getting the reward. And now we're going to talk about our implementation details, which Ege Tekiner will continue the presentation at this point.
Thank you. I am going to explain our general setup, our actual implementation, the cryptojacking malware in different devices, and our general data collection process. Oops, sorry. In our setup, it's based on a regular home networking settings. All the devices actually connected to only one gateway, internet gateway point, which is a router, and one computer inside the network was responsible from collecting the networking data. And compromised devices are also using the same networking pipeline to connect the CNC servers and the service providers outside the network. Here is our list of devices. As an IoT device to represent IoT devices, we use Raspberry Pi 4 and LG Smart TV. For regular daily usage devices, we use the laptop with a little bit average features. We also had a tower server which represents a powerful device, and we have a router that actually allows the devices inside the network to connect internet. In our dataset collection methodology, we use the same methodology for benign and malicious data collection, and we used actually our poisoning to reroute the data communication path to be able to collect the specific packages from specific devices. And we also labeled the collected networking data during the data collection process. So while we are making our data collection, we knew that if the data is malicious or not. So we actually used 3 datasets for our all experiments. For our first benign dataset and our second benign dataset and our malicious dataset. For our first benign dataset, we used the actually public dataset, and we basically downloaded it from a public repository. This dataset includes the interactive bulk data transfer, web browsing, video playback, and idle behavior user activities that actually we all doing every day. And here is the actually general dataset count, so our first benign dataset. In our second benign dataset, we created our own dataset from our own devices inside the network. So we actually collect the datasets with these idle behavior, web browsing, watching video from YouTube, large file download, and interactive user activities. But for the LG Smart TV, we could only actually collect data while we are watching video from different streaming channels due to, we cannot make some of these activities with the Smart TV. And in total, we had 16 different datasets inside our second benign dataset that we collected from 3 devices. And each 3 devices we actually represent 5 activities, and we also collected data from LG Smart TV. And here is the actual metrics are all our second dataset, benign dataset. And of course, the malicious data collection, which is the actually challenging part. For our malicious data collection, we needed to implement both in-browser and host-based cryptojacking malware to our all devices. So to be able to implement in-browser cryptojacking, we basically the first thing first, in-browser cryptojacking malware must use a actually service provider to connect and receive the mining tests, start performing crypto mining process. And cryptojacking malware, we use cryptojacking malware samples from different service providers like webminepool and webmine.io. And we created a basic WordPress server to actually deploy this different cryptojacking malware and test it in our lab environment. But actually, the challenging part for the in-browser cryptojacking was with the LG WebOS platform, because LG WebOS operating system does not support any WebAssembly or JavaScript libraries. So we use LG WebOS software development kits to actually cryptographic libraries to be able to implement a basic hash-based miner to implement cryptojacking malware. And we collected network traffic data at least 12 hours for every use case scenario during this in-browser cryptojacking malware implementation. For Raspberry Pi server and laptop, implementing host-based cryptojacking was straightforward because we actually use the binary minor gates, binary actual mining platform, and we run it in our each test devices. Minor gate allow us to actually use both terminal-based and UI-based mining, and we collected the data through with this platform. But implementing the host-based cryptojacking on LG Smart TV was again challenging, and the malware binary needed to be located in a suitable way again. And we use again LG WebHost development framework to create a basic IPTV application that runs cryptojacking as long as in the background, as long as actually the victim user using the app. Here is a basic screenshot from our IPTV app, and as you can see, there is some video is actually running in the front, but at the back side, the cryptojacking mining malware actually communicating with the CNC server to receive the mining tasks from a mining pool in this example. And in other example, we also created a CNC server that runs its own cryptocurrency node and create its own cryptocurrency mining tasks and send it to the IoT devices. So we eliminate the mining pool and create the node-based task sending for this malware. Here are our malicious samples. As I told you, we actually try the different set of experiments for our malicious samples and created this data set. So after that, actually, Dr. Ajar will explain, keep making the presentation.
Thank you, Ege. And after we collected the benign and malicious datasets, then we first wanted to do some initial observations on the raw dataset. And what we observed is that we saw that the highest malicious packet per second and average packet rates are for the malicious dataset is much smaller than the benign dataset. And this is what we see is that the malicious samples are trying to actually hide the communication and trying to minimize the communication. And on the other hand, we saw that for in-browser mining, the PPS and APS rates are very small, and compared to the binary mining samples. And for binary mining samples, we observed that APS and PPS rates are directly correlated with the computational power of the device. This means that for binary mining, miners are trying to maximize their benefit, their profit, as long as the device's power allows. And for all device types, we found that for in-browser mining, almost the same PPS and APS rates. So this means that the less communication. And when we come to our overall evaluation, we wanted to design we designed first set of experiments. And in the first experiment, that we wanted to design an IoT cryptojacking mechanism using machine learning. And then the second set of experiments, we wanted to design experiments to assess the different adversarial behaviors. And in the third experiment set, we designed experiments to assess various smart home network settings. And the fourth one is our goal is to assess the sensitivity of the classifier. Then in the first set of experiments, our goal is to design an optimum cryptojacking detection mechanism using machine learning. And it consists of the feature extraction, feature selection, and then in the last step, we wanted to decide the best performing classifier. And in the final step of this experiment set, we wanted to check the performance of our classifier for varying size of training sizes. And these are our we actually presented detailed results in the NDSS presentation, so I didn't want to go over in all of the details, but these are our results basically. And what we saw is the SVM is the best performing classifier in general. And then as you can see here, the data says we split the data for 12 hours, 6 hours, and 3 hours, and 1 hour data training sizes. And here are the results for those new training sizes. And some of the observations we can see, for example, for the accuracy is decreasing once the training size is decreasing to the point like 0.96. However, it's still not too bad. The results, I think, like more than 95% in general with even 1 hour training data. And for example, for the others, prediction time that we observed that in small devices is much less than the like a server kind of devices. And then in the second set of devices, in the second set of experiments, we wanted to assess the different adversarial behaviors that we can actually see in the real life. For example, the adversaries can target different kind of devices. It can be server, it can be desktop, or it can be an IoT device. And in the second scenario, we wanted to assess the different profit strategies. Like they can actually maximize the throttle value so that they can get the maximum benefit in a short time. In this one, we compared the different profit strategies, aggressive, robust, and stealthy profit strategies. And in the last scenario, we wanted to check the performance of our detection methods if the cryptojacking malware in browser or host-based. And here are our results. And in general, for example, from the first scenario, we can see that the best accuracy is obtained from the server. That means that if an attacker actually targets the server, there is a chance that the detection mechanism, there is highly a chance that the detection mechanism will succeed. However, on the other hand, when we look at the different profit strategies, we see that if a stealthy or robust approach are used, the detection accuracy is decreasing. And when we look at the third scenario, we can see that in browsers, cryptojacking malwares, they're in general using some CPU limiting techniques so that we can see that these techniques are actually working and it decreasing the accuracy of the detection method. And in our third set of experiments, we wanted to assess the different smart home settings, such as if an entire house, the devices, all of them are like a compromised. And in the second one, we wanted to test the partially compromised scenario in which we only selected IoT and laptop devices are compromised. And in the last one, for example, this is a more challenging scenario in which a single IoT device is compromised in a smart home setting. And when we come to the last scenario, we wanted to test all of the IoT devices compromised in the smart home. And when we look at our results, we can see that the challenging scenario, scenario 6 and scenario 7, the detection accuracy is actually decreasing. And however, if the entire house is compromised, we have better accuracy in general. And in the last set of experiments, we wanted to assess the classifier sensitivity, in which we test the scenarios for imbalanced dataset, classifier transferability, as well as the non-default parameters of the classifier. And for each scenario, we have a detailed explanation in the paper. And when we look at for example, scenario 8, we can see that even though there are different imbalanced data sets, we can see that the accuracy is the least is 97%. And this means that the features that we have decided in the beginning to design the optimum cryptojacking detection is actually giving high accuracy in different imbalanced dataset scenarios as well. And in the 9th scenario, that we can see the transferability between the different service providers. For example, let's say we trained our dataset with one service providers, and then we observe another service provider malicious activity, and we can actually still detect that. And in the last scenario, we tested for different classifier sensitivity, the different non-default parameters, and then even in this one, actually we can see that the classifier needs to be optimized, needs to be configured so that it can give high accuracy. It doesn't give very good accuracy for some of the parameters. So in this part, I will talk about our experimental challenge that we had throughout this study. And for example, as I explained, implementing cryptojacking on LG web was not straightforward for both in-browser and host-based cryptojacking malware. And we needed to actually go and check the code and in detail. And we used the LG web their own SDK in order to implement the in-browser cryptojacking malware. And then we implemented a IPTV application in order to deploy the cryptojacking malware on a smart TV. And also, I wanted to note that we actually, even though we shared all the data and the code, we did not share this part because it can be actually abused in the wild. So we didn't want to put that in the code that we share. And so the second experimental challenge is similar to the first one, in which actually we failed to expand our study for other devices. For example, Amazon Echo, Apple HomePod, Philips Hue environment. We also tried to implement the crypto miners on these environments. However, there was not enough implementation detail that how we can do it. So this could be another interesting perspective to follow up in the future work. And another experimental challenge that we had, because we had a very huge volume of data, the machine learning training was taking a very long time, even though we used very powerful servers in our lab, and it was still sometimes crashing, and we needed to repeat some of the experiments. And the last part is, at the beginning of this study, we considered to use the IP address in order to define the malicious classes. And however, we found that the IP addresses are dynamically changing during the mining process, and it's not easy to assign an IP address to a malicious identifier. Instead, we use MAC addresses so that we assume that if the device is mining, even though one application is doing mining operation on one device, we define that device as a malicious class. And in this one, we still think that if there's a research on this one to continue, and if it's done correctly, then this can be actually the malicious IP addresses can be also detected. And we shared all the code and data on the GitHub, and I wanted to just show some of the code snippets for how the data can be used. And this is a Python code, and for example, here we show how to include all these data sets that we have. And here we show we use the MAC addresses as an identifier for each device. And in the last one, this is a Python code. This is the Jupyter Notebook Python code. So the results are also there, and it can be easily seen by anybody just clicking the link. And also if you download it in the local, and you can easily reproduce the results. Of course, I think it should be on a very powerful computer. And concluding remarks. So we designed a novel, accurate, and robust IoT-based cryptojacking detection system. And we designed some novel experiment scenarios in which we collected both malicious and benign data. And we tested different adversarial behaviors as well as different network settings, which could be actually seen in the real life. And our dataset and the code are publicly available in our GitHub page of our lab. And you can actually use the QR code in order to see the web page. And the link is also available. And thank you very much for listening our talk. And I'll be more than happy to answer if you guys have any question. And this is our team, Ege Tekiner, myself, and Dr. Selçuk Uluağaç. And you can see the other projects as well as in the link that the labs link. Thank you.